Hi, we're going to start with talking about perpendiculars in space. This is section 10.3 in your book. We're going to start with some definitions and some theorems. So proofs of theorems in space are very much like proofs in a plane. You can use all of the theorems that you already know for planes as long as each is applied to a single plane. So let's look at some definitions. First of all, the perpendicular planes are two planes that form right dihedral angles. When we talk about perpendicular lines, they're lines that form right angles in the plane. Dihedral angles, remember, have a common line as their edge. Think of like 2 pages of a book. And then we have a line perpendicular to a plane is a line that intersects the plane and is perpendicular to every line in the plane that goes through that point. I'm going to show you some pictures of these as we look at the theorems in just a bit, so let's just get through these definitions and then we'll keep going. Alright, and the third one is a perpendicular bisecting plane of a segment is a plane that bisects a segment and is perpendicular to the line containing the segment. So let's look at some theorems, and I have some pictures to go along with them. Okay, here's theorem 10.2. A line perpendicular to two intersecting lines in a plane is perpendicular to the plane containing them. Now, if this line L is perpendicular to the line N, and then if I look at L and say, okay, and it's also perpendicular to the line M, then the theorem says that it must be perpendicular to the plane that contains them. Now, the definition of a line being perpendicular to a plane would be that that line, L in this case, is perpendicular to all lines that go through. So even if I drew another line here, all of the lines in this plane, if I just look at the single line and my line L, they would be perpendicular. That's what it means to be perpendicular to the entire plane. Okay, let's look at this next theorem. If a plane contains a line perpendicular to another plane, then the planes are perpendicular. Now, in red, I have the line AB. It's part of plane N, and it's perpendicular to plane M. So what it means to be perpendicular to plane M, it means that it's going to be perpendicular to any line on plane M that goes through B. Okay, you see, if it is perpendicular to the plane, that means the red line that's in plane N has got to be perpendicular to all of those lines that I've drawn in blue. I've just drawn a few of the lines. Now you need to picture that all of those lines in blue are on plane M. That's the horizontal plane. Now, the one that I did in the darker line right here, that's BE. So that means the red line, AB, is perpendicular to BE. And if that's the case, then this angle right here, from the red to this solid, thick blue, that's a right angle. Now, if you remember, the angle measure of a dihedral angle is the measure of the perpendicular lines to CD. So if I measure the angle, the dihedral angle, that's a right angle. It's 90 degrees. It's a right angle because this red line forms a right angle with all of these. But the one we're specifically interested in is BE, because BE and AB form an angle ABE, which is actually the measure of the dihedral angle itself. Okay, let me back up just a second. When we measure the angle of a dihedral angle, we have to measure the angle that's made by the red line here, which is perpendicular to CD, and the blue line here, which is also perpendicular to CD, but in the other plane. So the angle that we measure for the dihedral angle is this angle right here. And in this case, it is a right angle from what I showed you on the previous drawing. So if a plane contains a line that's perpendicular to another plane, then the planes themselves are going to be perpendicular. Okay, theorem 10.4 that says if intersecting planes are each perpendicular to a third plane, then the line of intersection of the first two is perpendicular to the third plane. So if you look at the red line I have here, the one that is the line of intersection of planes N and M, that line, because those planes are perpendicular to plane P, the line of intersection, which I have, that goes through A and B, and then below the plane, is going to be perpendicular to plane P. Okay, theorem 10.5, if AB, which is this vertical segment, is perpendicular to the plane at B, and BC is congruent to BD, so I'll mark those down as congruent, then AC is congruent to AD. So what we're trying to prove is that AC and AD are congruent. Alright, so the actual proof of this is in the overheads masters you can look at. I'm just going to talk through it for our case here today. So I'm given that I've got AB perpendicular. Now the definition of a line perpendicular to a plane means that that line is going to form a right angle with every single line that goes through B. That means I have got right triangles here. I've got two right triangles. So I need to state that I have right angles, and then I need to state that I've got right triangles, and then because of reflexive, this leg is congruent to itself, and I can use LL to get two congruent triangles, and then CPCTC to get the third sides congruent. Okay, this next theorem is very similar. In its proof, we're going to use right triangles that are congruent. Every point in the perpendicular bisecting plane of segment AB is equidistant from A and B. So here I've got plane N, and it perpendicularly bisects segment AB, which means that two segments are the same length. Think of it, the one triangle that's below the plane. It also means that I have two right angles, because this line is perpendicular to the plane, which means it's perpendicular to every other line or segment in the plane. So now I've got right triangles again. These two triangles are right triangles. They share this, so again I can use LL and CPCTC to get AD congruent to BD. Now because I'm asked for the lengths, you need to use the definition of congruent to go from congruent segments to length being equal. Alright, here's theorem 10.7. We're not going to prove that, but I just need to put it out there for you. It says the perpendicular is the shortest segment from a point to a plane. That means point Q is the shortest distance to this plane, and it's perpendicular. That means there's not another point over here that's closer to point Q than P. A couple of definitions here. Parallel planes are two planes that do not intersect. Remember that when we had parallel lines don't intersect, but we had to give the caveat that the parallel lines had to be in the same plane. Otherwise we would get skew lines. And then the second definition is a line parallel to a plane is a line that does not intersect the plane. So we have a couple theorems that are going to come up that talk about parallel lines and planes. So let's look at those. Theorem 10.8 says two lines perpendicular to the same plane are parallel to each other. Alright, here's theorem 10.9. Here we've got two lines that are parallel, the ones with arrows here. If a plane containing one of them is represented here in this picture, then what's got to be true is the plane that contains one of these two lines is parallel to the other. That means these two vertical lines here are just trying to show that those two lines are parallel. If these are parallel, there's no way that this line is going to intersect this plane, no matter how I rotate it, as long as that plane contains this. There's no way that this line will ever cut through this plane. Alright, here's a theorem that should make sense. A plane perpendicular to one of two parallel lines would also be perpendicular to the other one. So if this plane is perpendicular to this line and my lines are parallel, it must be perpendicular to this one as well. Here's another theorem that makes a lot of sense. Two lines parallel to the same line are parallel. So if line A is parallel to line B, so A is parallel to B, and C is parallel to B, then A is parallel to C. That looks like the transitive property at work, and actually it is. Okay, here's the next one. A plane intersects two parallel planes in parallel lines. So this plane right here, I'll call it N. N is a plane that is intersecting these other two planes. Let's call this K and M. Now K and M are parallel. So K is parallel to M. N is not perpendicular. It's just any old plane that cuts through both of these planes K and M. Now what this theorem says is that this line of intersection here and this line of intersection here with the other plane would be parallel. So this one says two planes perpendicular to the same line are parallel, which means if this is plane N and this is plane K, plane N and K are parallel because they're both perpendicular to the same line. This theorem goes along with the last one. The picture actually looks the same, doesn't it? It says a line perpendicular to one of the two parallel planes is perpendicular to the other also. So if I know this one is perpendicular to this plane, and if these planes are parallel, I know it must also be perpendicular to this plane. Okay, here's the last theorem. Two parallel lines are everywhere equidistant. That means if I measure the distance between two planes, now remember when we talked about the distance between two planes or between a point and a plane, it's the perpendicular distance. That means this is perpendicular. The shortest distance has to be the perpendicular distance, and actually this would be perpendicular as well. So it's the same distance over here from A to B as it is from D to C. If they're not the same, then if you thought about one plane being tilted a little bit so the distance isn't the same everywhere, then eventually those planes would run into each other and then they wouldn't be parallel anymore. Okay, so that was sections 10.3 and 10.4. It was a lot of theorems, a lot of things to kind of wrap your brain around. Now the good news is that in your assignment for 10.3 and 10.4, there are no proofs at all. The questions in section 10.3 are just going to be kind of testing how well you understand the different theorems. So don't be afraid to refer back to either this video or the overhead masters or the pictures in your book so that you can answer those questions. They're just going to be questions for you to answer. And then in section 10.4, it's going to ask you to do a lot of sketching. You have to sketch, you have to disprove some false statements by sketching a picture. So do your best, see if you can get something that works, and then I want you to take a look at the solutions and kind of just see how you did with those sketchings. We've talked about this before, but it is very difficult to sketch three-dimensional scenarios for a lot of people, myself included. So just do your best on those. Okay, that's it for this video. I'm going to do another one for the third section. So come back and look at that in a little bit.